Welcome back to lesson U2A7 where we discuss the intersections made between two planes. So far we discussed three main cases when two planes intersect along a line at a certain angle, when two planes are parallel to each other and they have no common points of intersection, and when two planes are coincident where every point on the plane is an intersection point. In the second video, we are going to take a look at how to use the normal to a plane to determine how the two planes are related to each other and the number of possible intersection points. Recall that the normal to a plane is perpendicular to any vector on the plane. And if we have two planes, pi1 and pi2, with their respective normals n1 and n2, if normals are scalar multiples of each other, which means the normals are parallel to each other, therefore, we're going to say that we will consider two cases. Case number one is the planes may be coincident, which produces an infinite number of points of intersection, or the planes may be parallel to each other, which provides no points of intersection. If n1 is different than kn2, which means the normals are not a scalar multiple of each other, so normals are not parallel to each other, then we'll say that the planes will intersect along a common line of intersection, and therefore we'll have an infinite number of points of intersection. So we're going to take a look at a few examples to see how the algebraic solutions can explain the intersections made between two planes. Obviously, in this case, we're going to use the normals to each plane. And in the first system of equations, we are given the planes pi1 and pi2. And their equations are given in Cartesian form. So in order to discuss the number of possible points of intersection, first we'll check their normals. So for plane pi1, normal n1, recall how we find normals, the coefficients of the variable terms. So coefficient of x will make the x-coordinate of the normal, coefficient of y makes the y-coordinate of the normal, and coefficient of z makes the z-coordinate of the normal. In the same way, the normal n2 will have the coordinates 2, 2, negative 2. There are different ways of how to determine whether scalar multiples of each other. So my favorite and quicker way is by finding the ratios of the respective coordinates, which means finding 2 over 1, so the ratio of the x-coordinates, and then 2 over negative 1, the ratio of the y-coordinates, and negative 2 over 1, which is the ratio of the z-coordinates. So if you simplify them, we'll get 2, negative 2, which are different. So we need to have all of them equal to each other to say that they're scalar multiples of each other. In this case, we'll say that the normal n1 is not a scalar multiple of normal n2. So this is a quick way for us to understand or make a quick decision whether the two planes will intersect at every point, no points, or along a line. And this will be the case when the two planes will intersect along a line. So now we can understand, hopefully, the importance of why we use normals or analyze normals to two planes in order to determine the points of intersection. So we're going to solve this system with more confidence, knowing that this system of equations will produce the equation of a line. So let's get started. First, I like to write the equations of each plane. So we have x minus y plus z equals 3, and 2x plus 2y minus 2z equals 3 again. So I'm going to call them equations 1 and 2. Let's make this a perfect circle, because why not? And we have number 1 and number 2 equation. Now we're going to follow the exact same strategy as before, the elimination method. So I'll decide to eliminate the variable x. Remember, you can eliminate any variable of your choice. So In order to eliminate x, I'm going to have either exact same coefficient as in the second equation for x, or opposite. So I will multiply by 2 to have the exact same coefficient. So this will give 2x minus 2y plus 2z equals 6. Remember that you have to multiply by 2 every term on both sides of the equation. And I know that this gets overlooked at very often and gets forgotten, so be careful. Next, I'll write the second equation. Nothing has changed about it, so I will just copy it down. So next thing that I want to do is start eliminating. So I will have to subtract the second from the first equation so that I can eliminate the x term. So 2x minus 2x minus 2y minus 2y plus 2z minus negative 2z equals 6 minus 3. So here is a subtraction. So we have 0x minus 4y plus 4z equals 3. Or simply negative 4y plus 4z equals 3. And this is when we start telling a new story that we have never discussed before. So when after eliminating one of the variables in the system of two equations given in Cartesian form or scalar form, we obtain an equation with two variables, we understand right away that the two planes will intersect along a line. So I'm going to write a note in here. So it means that the planes pi 1 and pi 2 have a common line of intersection. Now let's think about it. How do we find a common line of intersection? So what is a possible equation we can use? So for lines, we have used equations in vector form, or we have used their parametric forms or symmetric equations. So in this case, what we are going to do is find the parametric equations of this line. Find the parametric equations. And there is a standard process that we use to find the equation or the parametric equations of this line. So let me write this down. I need to work on writing and speaking. I still find it a bit difficult. Equations. Okay, so this is how we find the parametric equations. I'm going to write the steps just for this one. For this part of the process, I mean, step number 1. We are going to let one of the variables be a scalar. And you can imagine, or you can think of it just like, for example, when you have the equation of a line with two variables. So for example, if you have 2x plus y equals 3. So in order to find the y coordinate, you give x a certain value and solve for y. Now, in a two-variable equation, like in a system of two equations, it's easier to just substitute x by a regular number, like a numerical value, give it a numerical value. But here, because we're going to have the equation of a line with an infinite number of solutions, then we're going to choose not just a numerical value, but a scalar, an unknown scalar value. So we're going to let z be some scalar t. With this, we have created the first parametric equation for one of the variables, for variable z. And then solve for the other variable. So for y. So now we have the equation negative 4y plus 4z equals 3 become negative 4y plus 4 times scalar t equals 3. So that means negative 4y would be 3 minus 4t. Divide by negative 4 every term, both sides of the equation, and we'll obtain y equals negative 3 over 4 plus 1t. This will produce the second parametric equation. In our case, the parametric equation for y. Step number 2, we'll have to find the equation for x. Now, when you think about it, because everything is logical and it should make sense, and that's the way math works, so there is a flow in the thinking process. If we have the parametric equation for z and for y, so how can we find the parametric equation for x? Look at the information given here. So we are given two equations, and we're looking at their common line of intersection, which means that in order to find the third coordinate, or an expression or parametric equation for the third coordinate, we may choose either equation 1 or 2 to solve for x. Remember that now we have y and we have z, and we may choose either the first or the second, but by looking at their coefficients, remember we will have to solve or isolate x at the end, I would go for equation 1. So we have x minus y plus z equals 3, become x minus, for y we have the parametric equation negative 3 over 4 plus t. And for z, we have the equation t, and that equals 3. So let's solve for x. We have x plus 3 over 4 minus t plus t equals 3. So minus t and plus t will simplify. So we have 3 minus 3 over 4, which gives x equal to, so remember that you can convert 3 over 1 into multiplied by 4, numerator and denominator. So 12 minus 3, which is 9 over 4. So we'll say that we just obtained the third parametric equation for the third variable, the variable x. Now, when you look at these three parametric equations, which I will rewrite now, so step 3, I will be creating the vector form of the equation of this line. I will line up the parametric equations first. So we have x equals 9 over 4 plus, since we don't see the t term, we'll write 0t. For y, we have negative 3 over 4 plus 1t. And for z, we'll have no constant, so 0 plus 1t. Now, recall that the constant numbers in the parametric equation will make for the starting point in the vector form of the line. So we'll say that x, y, z, so this x and this y and this z would equal, so the starting point, which is defined by the constants in each parametric equation, so we'll write that down, 9 over 4 for x, negative 3 over 4 for y, and 0 for z. And then plus the scalar t, and now we'll have to write the coordinates of the direction vector 0, 1, 1. And we'll say that voila, we got the equation of the line of intersection in vector form and in parametric form. And if you were asked to write the equation in symmetric form, you would know what to do.